Last speaker for the morning is Jim Gielen. He's talking about connectivity systems, etc.
Okay, thanks very much for organising this workshop and for the invitation. I'm going to talk about some work that I did this year with Rutger. So let me just explain where this comes from. So this is related to an older theorem that I proved with Bert Gerards, Neil Robertson, and Jeff Whittle. And we were looking at the excluded minors for the class of matroids of branch width at most k. And we showed that they all have size at most 6 to the k. This was quite an elementary proof, and it gave a surprisingly good bound. So the theorem I'm going to talk about today is related to path width. So minor closed classes of matroids with bounded path width, and we show that they have only finitely many excluded minors. So that's the new theorem with Rutger. And when you see that in comparison to the previous theorem, I can imagine you're all really underwhelmed for a couple of reasons. So for those of you who know the definition of branch width and path width, matroids of bounded path width are way more structured than matroids of bounded branch width. And also in the branch width case, we got a nice bound on the size, and here I'm only telling you that there's finitely many of them. In my defense, I've worked really, really hard trying to prove this theorem over 20 years. Like, I've come back to it a lot of times, and it's a really, really difficult thing to prove. So what goes wrong is the following. So connectivity isn't useful in this context. So for example, there are excluded minors that are series parallel. And normally, like when you're trying to prove an excluded minor type theorem, it's nice to sort of say that you've got some sort of connectivity, and then away you go and you start working in that direction. I can't even, if you give me a 2 separation in an excluded minor, I can't tell you an explicit bound on the size of the small side. I can't say that every 2 separation has one side with at most 6 to the k elements or something like that. And I can't even tell you that there aren't, I can't give you a bound on the number of nested 2 separations in an excluded minor. So we don't get an explicit bound on the size of the excluded minors. We just show that there's finitely many of them. So I think that hopefully the most interesting part of the theorem is going to be the strategy we use to prove it, which I think reflects the difficulty we spent over a long time trying to get the result. So I'm just going to give you this quick overview of the proof, but there's going to be a bunch of things I haven't defined, and most of the talk's just going to be defining those things. So we prove a result in the context of connectivity systems, which are something you get from matroids, but also from other objects. So we prove a result in a more general context. Within connectivity systems, there's a containment operation called domination. So one connectivity system dominating another. And what we show is that containment operation is in fact a well quasi-order when you're looking at a set of connectivity systems with bounded path width. So what it means to be a well quasi-order is that if I take an infinite set of unitary connectivity systems of bounded path width, one of them is going to be dominated by another. And then we use this result to prove another result about connectivity systems, and that is with a different containment operation. So this time I'm talking about restriction, and that result is talking about domination. This restriction is a more sort of natural notion of containment for connectivity systems. And what we prove is that when you're looking at the class of unitary connectivity systems with path width at most k, there's only a finite number of forbidden restrictions. And then from there, we derive the matroid theorem. So we show that there's finitely many excluded minors. And this last step is quite interesting. It uses the notion of connectivity intertwining, which is basically a theorem due to Rong Chen and Jeff Whittle. Okay, so for most of you, you won't have a clue what this means. There's a whole bunch of things I haven't defined, and the talk is really just going to be defining those things with hopefully a bit of motivation along the way. Okay. So let's start out with matroid connectivity. We've seen the definition, and most of us are familiar with it. So if I take a matroid, I can take the connectivity of a set X, it's just the rank of X plus the rank of its complement minus the rank of the matroid. In terms of represented matroids, what this tells you is you take the subspace spanned by the vectors in X, the subspace spanned by the vectors in the complement, and this connectivity is roughly telling you the dimension of the intersection of those two subspaces. So it's telling you how connected that set is to the complement. Yeah, there's a 1. There's always a 1. Oh, different people put +1s in different places. It's one of those things. So we're not really going to be focusing on representable things. So what's more important for me for this talk is the properties that this connectivity function satisfies. So it's unitary, and so it's a non-negative valued set function, and the connectivity of a set is at most its sides. And the reason I call it unitary is that that's equivalent to just saying that singletons have connectivity 0 or 1. It's also symmetric that the connectivity of the set X is the same as the connectivity of its complement, and it's submodular. So what are connectivity systems? Connectivity systems are integer, so I've got some ground set E, and then for every subset I have a non-negative integer weight, which I think of as the connectivity of that set, and it should satisfy two conditions, symmetry and submodularity. And so that's, in general, a connectivity system. In this talk, I'm mostly going to be talking about unitary connectivity systems. So I'm going to have the additional condition that singletons have connectivity 0 or 1. So here are some examples of connectivity systems. We've already seen that you get a connectivity system from a matroid. You could play exactly the same game and get one from a polymatroid, if you like. You can also get connectivity systems from graphs related to vertex and edge connectivity and what I'll call rank connectivity. So in the vertex connectivity case, the ground set's going to be the edge set of the graph. And for a subset of the edges, the connectivity of that set of edges is just going to be the size of the vertex boundary, the vertices that are incident with both an edge in the set and an edge outside the set. That's going to be the connectivity. In the edge connected, for the connectivity system we get for edge connectivity has as its ground set the vertex set of the graph. And if I take a set of vertices, its connectivity is just the size of its edge boundary. The rank connectivity is a little bit more, well, I guess less familiar. You start out by writing out the adjacency matrix of the graph. So I get a V by V matrix. And now if you give me a subset of the vertices, I get these two principal submatrices corresponding to the set X and its complement. And then I have these two connecting matrices. But those two matrices are just transposes of each other. And the connectivity that I get, so the connectivity of the set X is going to be the rank of one of those connecting matrices, taken over GF2, two-element field. And it may look a bit weird when you first see it, but it turns out that this is the natural notion of connectivity if you're doing things like vertex minors or pivot minors. So those two connectivity systems, the matroid connectivity system and this rank connectivity system, are both unitary. The vertex connectivity system isn't, because edges typically have connectivity too, right? They've got two ends, and it's typically, there'll be edges outside also in hitting those vertices. And the edge connectivity is worse. It's like, you can get nice connectivity systems related to vertex connectivity by just going to the cycle matroid first, for example. But there are other ways. And you can also find unitary connectivity systems corresponding to edge connectivity, but I won't go into that. Okay, so that's connectivity systems. Now what I'm going to talk about is the main definition, which is the notion of path width, which is a very natural notion. So what does it mean for a connectivity system to have path width at most k? It means I can order the ground set in such a way that all of the separations respecting that ordering are most k separations. So if I take the connectivity of E1 up to EI for any I, it's going to be at most k. And so it's a fairly natural notion. That's what it means to have path width at most k. Branch width plays a lesser role in this talk, and in the interest of time, I think I'm just going to skip the definition of bounded path width, bounded branch width, but I'm just going to admire my slide for 3 seconds because that took me a long time to write. Okay, so let's talk about one of the containment operations on connectivity systems. And that's restriction. But before I tell you what restriction is, I need to tell you what the connectivity between two disjoint sets in a connectivity system is. So I've got a set S and a set T disjoint in my connectivity system. What's the connectivity between them? It's the minimum order of a separation that separates S from T. And by that, I just take a set X in the system that contains S but not T. So why do I say that separates? Well, think of the partition you get from X. X and its complement, one contains S, one contains T. Right, so that's, so I just take the minimum order of a separation that separates S from T, and that's the connectivity between S and T, which is fairly natural if you think about things like Menger's theorem. Okay, so what's restriction? I have a connectivity system and I want to restrict to some subset X of the ground set. So now what I need to tell you is if you give me a subset Z of X, I need to tell you what the connectivity should be. And it's just going to be the connectivity in the original connectivity system between Z and its complement within X. Right, so I look at the connectivity in the original connectivity system, so I find the smallest order separation separating Z from the complement of Z within X. And that's the connectivity, and it turns out that when you do this restriction, you get a connectivity system. Okay? And there are some really nice things about this connectivity system that I can hopefully convince you of in a few slides' time. This containment operation is very nice. All right, so now we know all of the definitions required for one of the theorems. Namely, if I've got the class of unitary connectivity systems with path width at most k, that class is closed under restriction. That's fairly easy to see. And so I can describe that class by its forbidden restrictions, its minimal restrictions that have path width bigger than k, and this result says that there's only finitely many of them for any k. Is that clear? So one of the more interesting parts, I think, of this work is why that result implies the result for matroids. This is fairly easy and it uses standard known results. But if you haven't seen these results on connectivity intertwining, I think it's quite interesting. So I'll spend a bit of time on this. So I've got a matroid and it's got path width bigger than k. And that previous theorem tells me if I look at its connectivity system, it's going to have a small restriction with path width bigger than k. So I've got this small restriction in my matroid with path width bigger than k. But this matroid could be huge. So what I want to do is I would like to get rid of elements. So I'm going to take an element in the matroid, I'm going to try to either delete it or contract it, And what I would like to happen is I would like this restriction in the connectivity system to stay unchanged, which means that for each partition ST of X, I want that when I remove that element by either deleting it or contracting it, I keep the connectivity between S and T. That's what I want to do, and I want to remove as many elements as possible from out here, and hopefully get down to a small minor. The good news is that if I only look at one partition of X, you can. So for every fixed, if I fix the partition and I take my element E, I can either delete it or contract it and keep the connectivity. That's Menger's theorem for matroids, or Tutt's linking theorem. However, I want my choice, so I've got one of two things here. I need my choice to be consistent regardless of which partition I chose. And that's problematic. So for example, if I take this grid, if I want to keep, in terms of just vertex connectivity, the connectivity from the left to the right here, and I want to keep the connectivity from the top to the bottom, if I take an edge here, if I delete that edge, I'm going to reduce the connectivity from left to right, and if I contract that edge, I'm going to reduce the connectivity from top to bottom. So I've got two different connectivities that I want to keep, and there's a lot of edges here that I can't delete or contract, keeping both of them at the same time. Okay. The nice thing is there's this beautiful theorem due to Rong Chen and Jeff Whittle that tells you that the problematic elements, the elements that I can't remove, aren't too numerous. So if I look at the elements whose, how did I write this? Whose deletion reduced the connectivity in the blue case and whose contraction reduced the connectivity in the red case, that set of elements, its size is bounded by some function that depends just on the connectivities that I'm trying to keep. So I want to keep this amount of blue connectivity and that amount of red connectivity. They prove that the number of problematic elements is bounded by some absolute constant that just depends on the connectivities that I'm trying to keep. Okay, and as a consequence of that, we get this result that says that if I've got a small set of vertices in a matroid and I'm interested in the restriction of the connectivity system to X, I can find a small minor which gives me the same connectivity system when restricted to X. Because for each element out there, when I delete it, I get some problematic partition, and when I contract it, I get some problematic partition. If there was an enormous number of elements out there, I'd have an enormous number of elements corresponding to the same set of two pairs. And that would contradict Rong and Jeff's theorem. Okay? And this is a great theorem, because this theorem says that if you prove a theorem about connectivity systems, you get a theorem about matroids. I can just use this as a machine and get theorems about matroids easily. And the nice thing about connectivity systems is when you restrict in a connectivity system, you don't lose the connectivity between any two sets, because that's the way we defined it. So if I restrict in a connectivity system, I don't lose connectivity between two sets. Whereas if you delete or contract in matroids, you may or may not lose connectivity between two sets. And if you think about all the work you've done in various theorems you've tried to prove about trying to keep a bit of connectivity when you need it in a matroid proof, it's painful. But in connectivity systems, restriction gives it to you for free. So working in the world of connectivity systems is great. And this theorem enables you to go back again. Okay. So that describes pretty much most of the picture. The only thing that I haven't told you about yet is this well quasi-ordering result. And so what is this domination containment operation? Don't read the definition. So roughly what this is saying, so I've got a connectivity system L and a connectivity system K, and I want to say what it means for K to dominate L. roughly what it means is I can find an isomorphic copy of L sitting inside K. However, it's not just a restriction. Like with the restriction in this definition here, that would be an equality sign. So what I have is that the connectivity of a set here should actually be at least the connectivity of the associated set over here. Not equal, just at least. But if you're thinking about things like path width, if you imagine that this is some connectivity system with path width bigger than k, some constant k, and I find it sitting over here, if all the connectivities here are at least the connectivities I see here, then of course this still has path width at least k. And this is a restriction of the connectivity system k, and so therefore k has path width bigger than k. So domination is a very natural notion if you want to think about obstructions to width parameters. Okay, so we now know this theorem, and it's very easy to see why that theorem, the main theorem, implies so this is the well quasi-ordering result, and I want to prove that that implies this theorem that there's only finitely many forbidden restrictions for path width k. Why is that? Well, what you would immediately get is instead of forbidden restrictions, you get it immediately for forbidden domination. That's part of the definition of well quasi-ordering. Right, so if I've had like domination, that's not quite the right way around. Dominated? I need to learn English better. With the domination containment operation instead of the restriction operation, it's an immediate consequence of that result. And now, why does this work? It works because for every domination obstruction, there's only finitely many things on the same ground set that are freer than it. And so I just replace that domination restriction by all of the things that are freer than it. And as you see, restriction is already part of the definition of domination. I'm restricting to that set. So that's basically why the first result implies the second. Okay, in the last 2 minutes, I'm going to explain why, I'm going to just talk a little bit about a more general conjecture. And it's a conjecture I like a lot. And it's that domination is in fact a well quasi-order on the set of all unitary connectivity systems. This differs from the previous result that I wrote down because the previous result we proved is we have this when I'm talking about connectivity systems of path width at most k. But now I'm suggesting that actually that you don't need to bound the path width for the result to be true. When I explained this conjecture to Paul Seymour, he had the good grace to be surprised and not believe it, which I always enjoy when he's like shocked and like, that couldn't possibly be true. Doesn't that contradict all sorts of things we know? And then I told him this fact, that if you take a connectivity system with huge branch width, it dominates all small connectivity systems. And for those who know about tangles, the reason for this is you just take an independent set in the tangle matroid, and those things are highly connected and they dominate everything. So that's actually a very easy observation for people who know a little bit about branch width. And that means that this conjecture, to prove this domination well quasi-order conjecture, it's enough to prove it for connectivity systems of bounded branch width. We've proved it for bounded path width, and path width, that's like paths, and branch width is like trees, and so it's not too hard to imagine that in the next few years we should hopefully be able to prove the conjecture in general. It's not such a big step, I hope. Okay, I'll leave it there. Thank you.
Thank you, Jim. Any questions?
Yep.
Could you say Could you say a few words about your proof strategy of the main theorem? The domination is well quasi-ordered.
Okay, so when you see a statement like domination, so you see a well quasi-ordering result on bounded path width or bounded branch width, the first thing you would think of is using the classical techniques of Nash-Williams and for like the minimal bad sequence argument. And it turns out that that doesn't easily work directly. So what you need to do is to argue, basically ask, I've got this infinite anti-chain. What are the properties there that would absorb all other connectivity systems of that kind? So sort of understand the universal objects of the kind of structure you're looking at. And it's going to be hard for me to explain what that is, but in this result, here, things of large branch width are universal because they absorb everything. But I'm only looking at things that have bounded path width. So for the fixed path width, what are the universal objects that would contain all things of some fixed size? So we characterize that. And then you can now say, well, none of my connectivity systems contain this universal object, and so they have a simpler structure. And we write down that structure, and then we ask, well, what's universal for that structure? And we repeat. And what you need to know is that you don't have an infinite chain of descending structures. Like I can't, so I have to stop at some point. My structure gets simplified every time I ask what's the most universal thing of that kind, and I don't have it, and I get a simpler structure. And you just can only refine things finitely many times. I don't know if that helped, but that is what we did.
First question is, can you relax this unitary condition to, let's say, f of x, lambda of x is at most twice x?
I think that's a good question, and I kind of imagined it would be easy, and then I thought about it, and it wasn't easy, so I just left unitary there. It would be a lot more work. It's complicated because, I mean, at the first step, for example, having high branch width wouldn't be enough, because if my connectivity system had, so if I had one connectivity system with only elements of connectivity 2, sorry, a big unitary connectivity system, and one where lots of elements have connectivity 2, the big one with the connectivity 2 isn't going to embed in the one with connectivity, where the elements have connectivity 1. And so it just gets messy. So I don't know what the answer is, but it's messy.
Another question, does your theorem also imply that graphs of bounded linear lengths are well co-ordered by pivot minors?
Yes, because you've proved that you have connectivity intertwining for pivot minors and vertex minors.
Oh,
so
yes. Bounded number of forbidden.
So I guess I should have said, no, I haven't proved that, but you have.
And also, I imagine that your earlier strategy for proving well quasi-ordering for matrix bounded branch width you must have tried using similar framework. Something fails completely, or?
Yeah. So it's very difficult to control. I mean, there's the separations you get because of the tree structure, but it's very hard to get any control on the other separations. And so, like when you put things together, there can be sneaky little separations that go through your structure in a funny way that don't behave like you were expecting.
Any more questions? Okay, well, let's thank Jim and all the morning speakers again.